Welcome to the Phenomenological Alliance channel. In this video, we will discuss the next question that phenomenology problematizes in the field of natural sciences, namely the issue of the evaluation of historical research.
Discussions about the existence of the speed of light have a long history, dating back to the philosophical schools of antiquity. However, with the acceptance of the view that light is a natural phenomenon that can be studied independently of the visualization process, methods for experimentally measuring the speed of light were gradually developed. The first quantitative estimate of the speed of light was provided by Ole Romer in 1676. Romer noticed that the duration for Jupiter's moon to emerge from Jupiter's shadow depends on the distance between the Earth and Jupiter. In conjunction, the eclipse of Jupiter's moon lasts about 1,000 seconds longer than in opposition. When the Earth is closer to Jupiter, the light takes less time to travel from Jupiter's moon than when the Earth is farther away from Jupiter. Using trigonometric ratios, it is possible to determine the speed of light. In 1727, the English astronomer James Bradley introduced a method to measure the speed of light by observing the aberration angle of stars. During one part of the year, a star can be observed through a telescope eyepiece without any correction, while in another part of the year, the telescope must be rotated at an angle so that the star is precisely centered in the eyepiece. This correction is necessary because light requires a different amount of time to reach the observer at different times of the year. By establishing a trigonometric proportion between the speed of light and the speed of the Earth, and knowing the required correction angle, one can calculate the speed of light. In 19th century, physicists determined the speed of light using physical methods.
The setup as used by Phys consists of a beam of light directed at a mirror 8 kilometers away. On the way from the source to the mirror, the beam passes through a rotating cogwheel. At a certain rate of rotation, the beam passes through one gap on the way out and another on the way back, but at slightly higher or lower rates. The beam strikes a tooth and does not pass through the wheel. It is noticed that at some rotation speeds, the white dot on the screen is visible, and at others it is not. Knowing the distance between the wheel and the mirror, the number of teeth on the wheel, and the rate of rotation, the speed of light can be calculated. The method of Foucault replaces the cogwheel with a rotating mirror. Because the mirror keeps rotating while the light travels to the distant mirror and back, the light is reflected from the rotating mirror at a different angle on its way out than it is on its way back. This is evident in the variations in the length of the light beam. At lower rotation speeds, the length of the light beam on the screen is shorter. As the rotation speed increases, the beam becomes longer. From this difference in angle, the known speed of rotation, and the distance to the distant mirror, the speed of light may be calculated.
Let's include the visualization process in the mentioned experiments. Let's pay attention to the sketch of Romer's method. It turns out that we are observing Jupiter from the moon. In reality, we observe Jupiter from Earth in such a way that Jupiter is apparently larger the closer it is to us. Closer objects appear larger the closer they are to the observer. Consequently, Jupiter's shadow is of different size. When observing an object behind the index finger with one eye, we notice that the object enters the field of view more quickly as the screen gets closer. This phenomenon is known as parallax, describing the rules of perspective change in motion. And vice versa. The screen can be stationary while the object is moving. As we are on a rotating Earth, the Jovian satellites require different times to emerge from Jupiter's shadow, in conjunction and in opposition. Practically, Bradley's method also involves different perspectives in various seasons, with the additional aspect that the image is observed through a tube, namely a pinhole camera. The pinhole camera limits our field of view. The fact that an object viewed obliquely is not visible cannot be attributed to the speed of light, but rather to the rules of perspective. While astronomical methods of measuring the speed of light involve rules of perspective, physical methods involve moving parts that interrupt the observation of the image. When observing a car wheel, varying speeds of rotation give the impression of different speeds or directions of rotation. This phenomenon is known as the stroboscopic effect. Understanding the Fizeau experiments boils down to understanding the stroboscopic effect. In the Foucault experiment, the same phenomenon is at play, with the additional aspect that the stroboscopic effect is observed on the screen. In the same way, steelwood fireworks create the impression that the bright trail is longer with an increased speed of rotation. We notice how the existence of the belief that Rome's experiments from 1676 measures the speed of light led to the development of more modern experiments, bringing us back to the question of phenomenological methodology.
Phenomenology, as a method, does not proceed from the position that accepted convictions are true. Phenomenology tries to raise awareness of reality, taking into account that accepted convictions can be the result of many causes: habits of thinking, inability to change attitudes, desire to stay in the comfort zone, etc. All these reasons can be reduced to the fear of facing reality. The same holds true in the field of natural sciences. Phenomenology does not proceed with the assumption that accepted scientific positions are true. Instead, it investigates how these positions become accepted. In the phenomenological approach, the study of the history of science, and history in general, acquires the utmost importance.
Regarding the speed of light, its existence isn't scientifically confirmed, but remains a hypothesis, plausible only if we assume that light is the same as a radio wave. The remaining experiments involve either the measurement of the speed of radio waves, or, for example, cavity resonance, interferometry, and similar methods. Therefore, let's phenomenologically explore whether light is indeed electromagnetic in nature.